Welcome to our first video on thermodynamics. Thermodynamics is an incredibly powerful subject. In fact, it's probably the most generally applicable thing we talk about in this entire course. It's almost certainly correct, by the way, so quantum mechanics may or may not be true. It'll certainly be modified as we go forward in time, but thermodynamics is probably totally fine. The word itself comes from thermo, meaning heat, and dynamics, meaning motion. And it arose from the idea that you could burn coal or burn wood, and you could use that to heat water and turn it into steam, and that expanding steam then could be used to drive, say, a piston and make a train go. So if you want to go off to Hogwarts, right, you're going to need to put coal in your train, and maybe some magic too. So before we get too far, we should probably discuss some fundamental ideas we saw in the thermochemistry chapter. And if you remember in the thermochemistry chapter, which I think was chapter 6 or 7 of our book, we used the symbol Q, and Q represented heat. And we were always interested in Q reaction, which was the heat that a reaction gives off or absorbs. And we noticed in this chapter that enthalpy change was exactly equal to Q reaction under conditions of constant pressure. There's a little bit more to it than that, but essentially that is true. So we calculate the change in enthalpy because that gives us the heat given off by a reaction or absorbed by a reaction under conditions of constant pressure. Remember, we have some terms here. So if delta H is negative, that means that heat is giving off, and we call that exothermic. You might say, well, why is it negative? Well, the reaction is losing heat. And of course, if we are around the reaction feeling that heat, it feels hot. If delta H is positive, the reaction is gaining heat, and it's gaining heat from the surroundings, so it's making the surroundings feel colder, and we call this endothermic. In fact, in thermodynamics, we can define the universe as being basically everything there is, and we can partition the universe into two sections, the system and the surroundings. And almost always in chemistry, the system will be a chemical reaction, and the surroundings will be everything else, maybe just a few meters outside of the reaction, but I suppose we could go to the edge of the universe if we wanted to. And so heat is flowing between the reaction and the surroundings. So in an exothermic reaction, it is coming out. In an endothermic reaction, it is going in. There was a law of thermodynamics that we called the first law of thermodynamics that said essentially the energy of the universe is exactly equal to a constant. Another way we can write this statement is to say that the energy of the universe is a constant, and so there can be no change. We can write delta E universe is exactly equal to 0. Now, the universe itself is a pretty big place, so we normally divide it up into the surroundings and the reaction. So we can restate this as the change in energy of the system or the reaction plus the change in energy of everything around the reaction is equal to 0. Or if you prefer, if we want to know the change in energy of the reaction, it is exactly equal and opposite to the change in energy of the surroundings. So we can look at either the surroundings or the system's energy change, and we can relate one to the other. This brings us on to something new, but I think we probably recognize the word spontaneous and non-spontaneous. And in thermodynamics, spontaneous means that something can occur without the input of energy. I mean, we can choose to put energy in if we want to, but if we don't, then it will still occur. So for instance, a ball will roll down a hillside, and so if we have a ball at the top of the hillside, it will spontaneously roll down. Non-spontaneous means that it will not occur without the input of energy. So it will not occur unless we put in energy. So that's not to say things can't happen. So for instance, if a ball rolls to the bottom of a hill, it can actually get back to the top. We just have to push it, right? We have to put in energy, and we have to supply energy to push it all the way back to the top. So non-spontaneous doesn't mean it can't happen. It just means it won't happen by itself. We just have to put energy in there. Case in point, you probably have a device in your house that is very non-spontaneous, and that is a refrigerator or a freezer to keep your drinks cold or your whatever it is, your Boca burgers frozen. And it's non-spontaneous, but it still freezes, it still cools things off. You just have to put in energy. So you plug it into the wall and use electrical energy to make it happen.